Welcome to this video where we will learn about rational and irrational numbers. So what is the difference between a rational and irrational number? In order to answer that question, we need a few definitions. So the definition of a rational number is a number that can be expressed as a ratio in the form a over b, where a and b are integers and b is not equal to 0. The rational numbers include the integers, fractions of integers, and any number with a terminating or repeating decimal expansion. So the important parts from the definition: ratio of integers. Good way to remember this, looking at the word rational, is the root word ratio. A rational number can be expressed as the ratio of two integers. So let's list a few examples of rational numbers. So we can start with integers. So 4, -11. Now, even though they are not in the form a over b, right, ratio of two integers, we could easily turn them into a ratio of integers. 4 could be expressed as 4 over 1, -11 over 1. Now we have the ratio of two integers, so 4 and -11 would classify as rational. Then we have fractions of integers, so we could say 1/2 or 7 over 5. Those would be rational numbers, ratio of two integers. A terminating decimal, so 0.13. That's a rational number. A repeating decimal, 8.6 repeating. Now, how we would express the decimal examples in the ratio as a ratio of two integers will be something we look at in the next two slides. But these are all examples of rational numbers. So then an irrational number is a number that cannot be expressed as a ratio in the form a over b, where a and b are integers and b not equal to 0. Essentially, any number that cannot be classified as a rational number is then irrational. The decimal representation of an irrational number does not terminate or repeat. So based off that second part of the definition, the most famous irrational number that we have learned is pi. Pi's decimal expansion is 3.14, and it continues on, never terminating, never repeating. But what are other examples of irrational numbers? Well, to create some more examples, we're going to have to use square roots, which we've been using in the previous videos. So if we have, say, the square root of 2, so the radicand is not a perfect square, well, then the square root of 2's decimal expansion is 1.41, and it continues on, never terminating, never repeating, means it is classified as an irrational number. We could have the square root of 8. That could be simplified into 2 square root of 2, but it would remain an irrational number. It has a decimal expansion that never terminates or repeats. So let's make note here. Not a perfect square. So if we have a square root expression where the radicand is not a perfect square, we would classify it as irrational. So if we go back up to our list of rational numbers, let's add the square root of 9. 9 is a perfect square. Square root of 9 is 3. 3 is a rational number, so square root of 9 is rational. So we can make note here that the radicand was a perfect square. So this is helpful because now we have more examples of irrational numbers other than pi. Now the next piece, often students misstep when they're looking at a fraction, say pi over 2. And they go, okay, that's in the form a over b, so wouldn't that make it rational? But this is where the second part of the definition comes into play. It has to be the ratio of integers. And since pi is not an integer, even though pi over 2 is a ratio or a fraction, it would still be classified as irrational because it is not the ratio of two integers. Same thing if we saw square root of 2 over 4. Again, it's a fraction, a ratio, but it is not the ratio of two integers. So it would be classified as an irrational number. Now let's take a look at those decimals. How can numbers expressed as either terminating or repeating decimals be represented as the ratio of two integers? And we'll start with the terminating decimals. Say we wanted to express 0.3 as a ratio of two integers. That would help classify it as a rational number. So we can express 0.3 as 3 over 10. Right? 3 is in the tenths place. 3 and 10 are both integers. Ratio of two integers means that 0.3 is rational. Now we can move to 0.86. So we'd have 86 over 100. That could reduce to 43 over 50. In either form, it's the ratio of two integers. So 0.86 is rational. What if we had 2.419? So we'd have 2,419 over 1,000. Again, ratio of two integers. And we can do this for any terminating decimal. All that changes is the factor of 10 that we have to use in the denominator based off of how many decimal places we go to. Now for repeating decimals, a little bit harder. We need to follow an algorithm or use a technique in order to show that a repeating decimal can be expressed as a ratio of two integers. So if we want to express 0.2 repeating as a ratio of two integers, the first thing we're going to do is define x to be the repeating decimal. So 0.222 repeating. Now I wrote it a bit differently to include a couple of more 2's after the decimal before I put the repeating bar on top so that the work will make sense. Next thing we're going to do is multiply this by a factor of 10. So then that gives us 10x equals 2.222 repeating. The advantage of doing this now is we've moved the decimal place 1 unit to the right, but on the right side of the decimal, if we compare the two equations, all the 2's line up. And this is where the idea of infinity and never-ending decimals can bend our mind a little bit, but both of these equations have the same number of 2's on the right side of the decimal place. So let's use that to our advantage. So we can subtract the x equation from the 10x equation. Now what happens on the right side of the decimal is all of these 2's simplify or cancel with one another. So on the left side we get 9x, on the right side we get 2, and that means x equals 2 over 9, which is the ratio of two integers. So 0.2 repeating is equivalent to 2 over 9. What if we had more repeating decimals? So in this case, 0.39 repeating. Very similar. So we're going to start by saying x equals 0.3939 repeating. If we try to multiply by a factor of 10, like we did above, we're not going to move the decimal enough units. Remember, we want everything on the right side of the decimal to line up so that when we subtract, they simplify or cancel. So here we need to multiply by a factor of 100. So 100x equals 39.3939 repeating. Then we can subtract the x equation from the 100x equation, being sure to line everything up carefully. On the right side of the decimal place, all the 3 9's simplify or cancel. So we get 99x equals 39, which is x equals 39 over 99, which can reduce to 13 over 33. So that means 0.39 repeating equals 13 over 33. Now, this algorithm, this technique varies as the repetition changes. So if we had more units, more decimal places repeating, or let's say the repetition was only on the 9 and not the 3 and the 9, it's going to vary a little bit. I would encourage you, if you find this interesting, to look at more resources to find out how that would work. But for our purposes in this video, just knowing that this method exists to turn repeating decimals into the ratio of two integers is the conclusion that we want to make, because then that allows us to classify repeating decimals as rational numbers. So now let's classify some numbers as rational, irrational, or maybe we can't determine either way. So first example, negative 17. Negative 17 could be written as negative 17 over 1, means that is rational. Square root of 196. 196 is a perfect square. Square root of 196 then is 14, makes that number rational. 20.176, terminating decimal. That means it's a rational number. Square root of 9 over 25. So square root of a fraction. So we'd say square root of 9 over square root of 25. Remember how we could break that up, which is 3 over 5. Again, we have a rational number. Square root of 96. 96 is not a perfect square. So square root of 96 then would be an irrational number. 0.92 repeating, with only the 2 repeating. It's a repeating decimal, so therefore it would be rational. 84.10928 ... So the 3 dots indicate that the decimal expansion never terminates, but the problem is we don't have enough information to know what comes next. Could it be that it repeats the 10928 over and over again? Could. That would make it a repeating decimal, which then would be rational. Or could it be just a random sequence of numbers that continue on, which would make it non-terminating, non-repeating, and irrational? Well, that could be true too. So we don't have enough information here to figure it out. So we'll say cannot be determined. Okay. Then we have 3 pi. So pi is irrational. 3 pi then, still irrational. And then the last one, we have this expression, square root of 36 plus square root of 100, which we can simplify. So that's 6 plus 10, which is 16, and that's a rational number. Okay, so here, the highlights, if we have a square root expression where the radicand is not a perfect square, that would be classified as irrational. Pi is irrational. And in number 7, the 3 dots indicating that it never terminates doesn't give us enough information to classify that number either way, as rational or irrational. Now I want to make a note on the calculator. Imagine we were using a calculator to help us determine if a number was rational or irrational. So I have a screenshot of a calculator screen with a couple of numbers input. So the first being pi. If we look, type in pi, hit enter, the calculator reads out 3.141592654. Now we had a discussion that pi is a non-terminating, non-repeating decimal, yet on the calculator screen, it looks like it terminates. And a terminating decimal would be classified as rational. And that's based on the limitation of the calculator. It can only show a certain number of decimal places in a decimal expansion, and then it stops. It either stops or it rounds. So we just have to be careful to relying on the calculator to help us make this decision. Same thing, square root of 7. 7 is not a perfect square, so we would go under the assumption that the square root of 7 is irrational. Yet if you're not sure and you go to the calculator, you would see a terminating decimal. It stops. Okay, we just have to be careful there. 2/3, that's a rational number. It's a repeating decimal. It's 0.6 repeating. But notice the calculator actually rounds it at the end because it can't keep going. It says, all right, I'm just going to round this last digit. So be careful. We cannot conclude that these numbers are rational or irrational based solely on the calculator, as it only displays the first 9 digits of the decimal expansion. And I'm basing this off of TI-84. Maybe there are calculators that show more digits, but they're still going to run into the same limitation. The number could be a rounded terminating decimal or a rounded non-terminating repeating decimal, both of which would be classified as rational. And then alternatively, it could be a non-terminating non-repeating decimal, which would make it irrational. Right? So just be careful. We really have to know the definitions of rational and irrational. The calculator isn't going to help us with that decision. Lastly, determine if the following numbers are rational or irrational and explain your reasoning. So we have square root of 12 over 3. So this is a ratio, it's a fraction, and we had this discussion on the first slide, so it's nice to bring it back on the last. The issue is square root of 12 is not an integer. And the definition of a rational number is a number that can be expressed as the ratio of two integers. So since square root of 12 is not an integer, the square root of 12 over 3, that number is irrational. Now, if we look at the next example, square root of 12 over the square root of 3, well, square root of 12 is not an integer, square root of 3 is not an integer. But we can simplify that before we make our decision. And that's the key for classifying this value. This is really equivalent to the square root of 4 when we divide the radicands, which is equal to 2 because 4 is a perfect square. That means that this number is a rational number. But if we did not simplify, we would have classified it incorrectly because we would have said square root of 12 is not an integer, square root of 3 is not an integer, so that number is not the ratio of two integers. So the conclusion we need to make here is be careful. If we can simplify, or if there's something that can be done before the classification happens, we should do that, so that then we can make the correct decision on whether the number is rational or irrational. So go over the definitions of rational and irrational numbers, practice identifying whether numbers are rational or irrational. It's new, so it's going to take a bit of repetition, and then continue into the next video where we're going to explore what happens when we start adding and multiplying rational and irrational numbers together. And I'll see you there.